Problem 116, populating next right pointers in each node. So to solve this problem, we need to know one concept, and that's BFS. BFS stands for breadth first search and is a graph traversal algorithm that searches the nodes at a given level before searching the nodes at a subsequent level. And by level, I mean depth in a tree. So consider a perfect binary tree like this. A perfect binary tree is where every node has exactly 2 children, and the leaves are all located at one level. As you see, they're on one level. So level 0 is going to be the shallowest depth, and we search this node first in BFS. Then we go to the depth of 1 to search the next 2 nodes. Then we go to the deepest level to search the remaining 4 nodes. We use this to our advantage when we solve this problem. We're given the example here of the given tree, and we basically need to point the right pointers of each node to its right neighbor. How do we do that? Well, let's just illustrate it off of the tree we're given with. 1, 2, 3, 4, 5, 6, 7. How many right neighbors? Actually, we could illustrate this by basically running through the algorithm. So what we're going to do is we're going to maintain the number of nodes to visit next in a queue. And a queue has a first in, first out structure, meaning the first nodes we put in are the first nodes we get out. So first, we have 1. We pop 1 from the queue so that the queue is now empty. And we extract the neighbors of 1 to put into the empty queue, in which case it's going to be 2 and 3. But the order at which we put the neighbors is important. This is because we always want to first consider the right child before putting in the left child. Because when we consider the right nodes first, we can store that value in a local variable, let's call it temp, which is going to be used to update the right pointer for its left neighbor. The rightmost node will never have any neighbors, but by keeping track of it, we know what to assign to its left neighbor. So to illustrate this, we just popped 1 from the queue. And now what we're going to do is we're going to add the neighbors of 1 to the queue, starting with the right node. We're going to add it to the left, so we put 3 here, then we add 2 right here. And if you think how this is achieved, if you're wondering, this is done using a deck in Python. So with that, we can go on to the next layer because we just popped the nodes in the next layer. We pop the rightmost value, so now we have 3, and 1 is assigned to none because temp always gets initialized to none when we go on each level. So now that we're on level 2 or level 1, temp is none again. When we pop 3, we know that 3 is the rightmost neighbor, temp is none, so 3 gets assigned to none. And we now put the neighbors of 3 into the queue, starting with its right child, which are going to be 7, then 6. And after we have done this, we can now pop 2. After we pop 2, we're going to have something that looks like this. But the temp variable just got updated to 3 because we just popped 3 from the previous iteration. So the right neighbor of 2 will automatically be assigned to 3. And we need to now append the right children first of 2 into the queue, then it's left. So it's going to now look like 4, 5, 6, 7, which you see where this goes. We iteratively continue this process until we have nothing left in the queue, meaning we've traversed the entire tree, and then we can return the answer. So with that, we can program it in Python. So we're going to be importing, so from collections, we're going to be importing a deck. And a deck is a queue structure that allows us to append and remove nodes from the left and right sides, which is exactly what we need. And if the root is none, we're going to return an empty list because it means there's no tree to traverse in the first place. Otherwise, we can continue. Queue is equal to deck, and we append the root to this queue. And we're going to then say, while the queue is not empty, it means there's more nodes to traverse. And so we can continue with the logic. We're going to get the length of the queue to tell us how many nodes there are in the current level, and we're going to initialize next node to be none, because we always consider the right child first, which by default has no next right neighbor. So for I in range of L, we are going to pop it. We're going to get the current node by popping it from the current queue. So queue.pop. And if cur_node.right is not none, it means we can add it to the queue. And specifically, we add it to the left. So cur_node.right. And the order that we do this is very important, because if you consider the left child first, it violates the rule of first in, first out. Because if we put the left child first, we're going to consider the left child first, and we're not going to be able to store what the next right neighbor should be in the temporary local variable. So with that, we can just say cur_node.next is equal to next node, and next node is equal to cur_node. And with that, that's the entire algorithm. So we can return the entire tree that is stored at the start of root, return root, and we're done. So let's run it. Is not valid. It's not a valid return type. If root is none. Wait, what does it say? If oh, I guess we could just return none. So we could do that. That works, so let's run it. Let's submit it. And there we go.